Hello students, welcome to the chapter 11 lecture, second to last one. We are almost there. So this is essentially a continuation of the previous chapter when we were looking at synthesis of alcohols. Now we're looking at reactions of alcohols. So here's your general list of the possible reactions that we're going to look at. You can dehydrate to an alkene, you can oxidize to an aldehyde or a ketone, you can substitute to form an alkyl halide, you can reduce to an alkane, you can do an esterification, you can do a tosylation, which is usually an intermediate step in a larger synthesis. And you can also do specifically a Williamson synthesis of an ether. Here's your general chart of the different reactions we're going to look at. Dehydration, oxidation, substitution, reduction, esterification, tosylation, and synthesis of an ether. So just a brief recap of oxidation states. You don't need to remember how to calculate oxidation numbers. But oxidation is losing electrons, reduction is gaining electrons, but you can also think about it as oxidation as gaining oxygen, and reduction as losing oxygen or gaining hydrogen. Okay, so when we talk about oxidation states of carbon, right, the most reduced state of carbon is just an alkane. And then primary alcohol, aldehyde, carboxylic acid, and carbon dioxide would be the highest form of oxidation. So the most oxidized carbon you can get is carbon dioxide. So when we talk about oxidizing, we're talking about going from alkane to alcohol to aldehyde to carboxylic acid to carbon dioxide. And if it's a secondary alcohol, then you can go alkane, secondary alcohol, ketone. And if you're a tertiary alcohol, you can't usually oxidize further than that. But that's what we're talking about when we talk about oxidation and reduction. So for secondary alcohols, they become ketones. And you use an oxidizing agent. Traditional one is just sodium dichromate in sulfuric acid, but chromium's toxic, so we use this sodium hypochlorite compound, NaOCl, in acetic acid, and that gets you the reduction, the oxidation to the ketone. So the way this works is, in the presence of acid, sodium dichromate will form chromic acid. And chromic acid can get deprotonated to form the acid chromate ion, and that's what does the actual oxidizing. So here's the mechanism. The first thing that happens is your chromic acid gets deprotonated and forms an ester with the alcohol. That's the chromate ester. Then you get deprotonation, formation of a double bond, and that kicks out the chromate ion. Okay? So essentially you're deprotonating that oxygen and allowing and stabilizing the negative charge so that the carbon can get deprotonated and form the double bond. For primary alcohols, these get reduced to aldehydes. If you use the chromic acid reagent, you get a carboxylic acid. So you need a more mild agent if you want to stop at the aldehyde. So for that we use pyridinium chlorochromate, which we'll just abbreviate PCC. So that's a complex of pyridine, that's pyridine, it's like a benzene with a nitrogen in it, that's pyridine, a chromate and chloride ions. Okay, so it oxidizes primary alcohols to aldehydes and secondary alcohols to ketones. So if you want to form an aldehyde from an alcohol, you don't need to write this part out, just write PCC in whatever solvent, doesn't really matter, and you get an aldehyde. You cannot oxidize tertiary alcohols because you'd have to break a carbon-carbon bond. So you can actually test for the presence of primary and secondary alcohols, because if it's a tertiary alcohol, you add chromic acid and you won't get anything, but if you had a primary secondary alcohol, you will. So sodium hypochlorite, NaOCl, can also reduce, this is bleach. If you weren't aware, sodium hypochlorite can oxidize alcohols. And also, since there's no acid involved, if you have a compound that might be acid sensitive, meaning if it was in the presence of an acid, it would react, you're going to want to use NaOCl. There's also something called the Swern oxidation, where you use dimethyl sulfoxide, or DMSO, oxalyl chloride, which is COCl2, and something, it says hindered base, so we talked about that, so triethylamine, so TEA, or, right, so nitrogen, so it's basically ammonia, but instead of hydrogens, you have ethyl groups. Okay, you can also get the reduction to an aldehyde. And you only need to use one, right? Here's another reagent that can do this. This is called Des-Martin periodinane, or DMP. So essentially, it's this wacky reagent. So you've got this kind of ring structure with an ester in it, and this iodine that's forming multiple bonds with some acetates on it, and that will reduce. Excuse me. That will reduce primary or secondary alcohols to aldehydes or ketones. There are a lot of different things you can use, so probably don't use the chromium. And you only need to remember one. Okay, so NaOCl, that's sufficient to oxidize to a ketone or an aldehyde. It says the most appropriate method. I'm never going to ask you most appropriate method. As long as you know one that works, it's fine. Yeah. So oxidation in biology is catalyzed generally by this giant compound called nicotinamide adenine dinucleotide, or NAD+. So that becomes NADH. So it like cycles back between NAD+ and NADH. And there are other ones. Ethanol gets, so when ethanol goes into your system, it gets oxidized to acetaldehyde, which then gets oxidized to acetic acid, which can then be metabolized. So there's a lot of reduction and oxidation that goes on in your body. So here's what NAD+ looks like. It basically reduces ethanol into acetaldehyde, and then you get reduced NADH. And then acetaldehyde plus water plus another NAD+, so it's a double reduction, gives you oxidation, gives you acetic acid. So it's a two-step oxidation. And it's actually, if you'll notice here, there's actually two different proteins. Same oxidizing agent, but two different proteins that are responsible for that. Methanol undergoes essentially the same thing, but it goes from methanol to formaldehyde to formic acid, and ethylene glycol gets converted to oxalic acid. And both of these are toxic. So that's why these get you sick. The methanol itself and the ethylene glycol themselves are not the toxic things. It's your body processes them, and then the products that end up popping out end up being the formic acid is not good for you. Shocker. Alcohols can act as nucleophiles. We've seen this before. Alcohols are weak nucleophiles, but if you can deprotonate it and form an alkoxide, that's a strong nucleophile. As an electrophile, the alcohol has to be protonated first. So if you protonate an alcohol, then water is a decent leaving group. So you can't just, an alcohol is not just going to leave on its own, but if you protonate it first, so in an acidic environment, if you protonate that alcohol, then it can leave as a water. Tosylate esters, so this is something you can do to an alcohol group. You can basically convert it to what's called a tosyl group, which we'll just abbreviate TS, okay? That's just a really, really good leaving group. So if you need an alcohol gone, or if you want to replace an alcohol with something, the easy way to do it is to first convert it into a tosyl group, and then that tosyl group will really leave. So you basically treat your alcohol with tosyl chloride and pyridine, geez, I can't talk today, pyridine, okay? And then that converts it to a tosyl group. Then you can have nucleophilic substitution because a tosyl group is a really great leaving group. You can also have elimination if you put it in a base. So this is a way to set up an alcohol for either a substitution or an elimination. So tosylates basically be replaced by anything. They're very, very. It's got a really good resonance structure, so it's an incredibly stable leaving group. So you can get a replacement with an alcohol, although if you're starting with an alcohol, this would be running in circles. You can get it replaced with a cyanide to get a nitrile. Halides can go on there. Alkoxides, ammonia can go on there, and then of course you can use this to reduce to the alkane if you want to, using lithium aluminum hydride, which we've seen before. So reduction, this is going the opposite direction. This is going from alcohol to carbon-carbon double bond. So if you have concentrated acid, you can obviously form a double bond, and then you can just hydrogenate that. Or you can make it a tosylate and hit it with lithium aluminum hydride. Again, if you hit it with some acid, then the alcohol, which is a bad leaving group, will get protonated into water, and water is a good leaving group. So if you hit it with a halic acid, so HCl, HI, whatever, or HBr, you can actually substitute in a halide, which you might want a halide there to do your next whatever your next reaction is. Okay, so what's important to note is tertiary and secondary alcohols will go via an SN1, and primary will go via SN2. Right? So just to reiterate the SN1 mechanism, you get protonation, and then that water will just up and leave and give you a carbocation, which can then be attacked by the halide. So that's tertiary and secondary will both do that. And keep in mind, secondary carbocations can rearrange. For SN2 mechanism, you get protonation, and then you just get backside attack, release of the water, all in one step. So for HCl, since HCl is a weaker nucleophile, you actually have to add zinc chloride, which promotes the reaction. So this gives us something called the Lucas test, where you have zinc chloride and concentrated hydrochloric acid, and it tells you what kind of alcohol you're dealing with. So the Lucas reagent basically forms a strong, it bonds to the oxygen, which makes it a better leaving group. So it makes it faster reaction. Secondary and tertiary alcohols react faster than primary alcohols, so based on the speed of the reaction that you get, you can determine what this is what we call structure elucidation. So we don't know what this thing looks like, so we run a couple tests on to say, is this here, is this here, is this here? So limitations of these kinds of reactions: primary and secondary is not great. Elimination competes with substitution. You can get rearrangements, and so it's not a great way to make alkyl halides. You're probably better off, if you're doing a synthesis, you're probably better off forming an alkene first, and then adding a halide to that. So 2-methylbutanol is treated with HBr, and you get 2-bromomethylbutane, right? So why is that? Well, you get a secondary carbocation, which then you get a hydride shift, which gives you a tertiary carbocation, so then your product is actually the 2-bromo. Phosphorus halides give you better yields. Okay, so for alkyl chlorides, you can use PCl3 or SOCl2. For alkyl bromides, you use PBr3. And if you want alkyl iodides, you use phosphorus and iodine, because this one doesn't really exist, so you can't just have that. You would just add, you would say phosphorus / iodine. So you've got neopentyl alcohol, you had PBr3, you get neopentyl bromide. You've got this alcohol, whatever this is, right? 14, 15, 16, so I don't know what that is. 16 carbon alcohol, phosphorus / I2, you get the iodide. PBr3, you get the bromide. So that's the general, probably the better way to do it, is to use the phosphorus halide. So the mechanism is actually the alcohol is the nucleophile instead of being the electrophile. The alcohol is the nucleophile, attacks the phosphorus, releases one of the halides, and it forms this complex, which is a very good leaving group. So then that halide will basically zoom back around, not attack that, it will attack the carbon and kick out that oxygen phosphorus halide mess. So thionyl chloride is your best bet to replace with a chloride. So thionyl chloride, SOCl2. But if you put PCl3, I'm not going to get mad. So again, what happens is you have nucleophilic attack on the sulfur from the alcohol, get a little bit of rearrangement that ends up kicking out a chloride, and then you get deprotonation to form this chlorosulfite ester, which is a very good leaving group. It spontaneously leaves and rearranges so that the chloride swaps over, and you get chloride attachment and sulfur dioxide. Dehydrations, we've looked at these. So in sulfuric acid, in concentrated sulfuric acid, you will get a double bond. It does go by an SN1 mechanism. You get a carbocation intermediate, you get the Zaitsev product. Bimolecular dehydration produces an ether. So that's important. So if you have two of these and they both dehydrate, you'll actually form a dimer with an ether. So you can actually, lower temperature favors ether formation, higher temperature favors alkene formation. So, right, same dealio. It's the E1 mechanism. So you protonate your water, water leaves, and then you get deprotonation of your carbon to form the double bond. We've looked at all this. This is all repeat from earlier chapters. It's the E1 mechanism. So, So here you can get rearrangement. Or you can get two possible products, but your major product is going to be the more substituted one. Bimolecular condensation to form ethers. Okay, so what happens is you get nucleophilic attack. So you do the same thing. This is an acid, right? And then you get nucleophilic attack that displaces the water, okay? And you form an ether, and then that gets deprotonated, and you get an ether. Okay, so a protonated alcohol can be attacked by the molecule of the same alcohol, and you'll end up getting a condensation of two ether molecules. Okay, vicinal diols, which remember geminal, vicinal, geminal same carbon, vicinals different carbons. So if you have two adjacent alcohols, okay, vicinal, geminal, vicinals can do two specific reactions that only vicinal diols can do. So one thing, this is called the pinnacle arrangement, and then periodic acid cleavage. That's not periodic as in a period. That's per iotic as in iodine. So the first thing is the pinnacle arrangement. Basically what happens is you end up with, you take pinnacle and you'll notice this methyl group goes away and you get a ketone here. So it's a dehydration, it's a dehydration because you get water as a product. So the mechanism is, first step, one of the alcohols gets protonated and then leaves. Okay, so you're forming a carbocation. Second thing that happens is you're going to get a methyl shift. Okay, methyl shift over, and then you're going to get you got some resonance here between the positive charge being on the carbon and the positive charge being on the oxygen. And basically what happens is you get a deprotonation of that oxygen and you form the double bond. That's the pinnacle rearrangement. It's similar to a lot of the other carbocation rearrangements we've looked at, but this one's somewhat unique in that you have you go from a vicinal diol to a ketone. Okay, periodic acid cleavage is you take an alkene, right? You form a glycol, right, vicinal diol, and you treat it with periodic acid, HiO4, and you get ketones and aldehydes. Okay, so we can already cleave alkenes, but let's say you're starting with vicinal diol, you can also cleave. You can do the same cleavage that way. Okay, so if you have this glycol, right, basically what happens is the iodine comes in, forms a bond with both of them, and they end up it ends up rearranging such that you break a carbon-carbon bond to form ketones or aldehydes on either side. So esterification is, right, remember an ester is like a carboxylic acid, but instead of having an alcohol, you have an ether. That's an ester. Right, and there are a couple ways you can make them. So you can do a Fischer esterification, which is an alcohol plus a carboxylic acid. You have tosylate esters, sulfate esters, nitrate esters, and phosphate esters. So Fischer esterification is, basically it's as simple as you have an alcohol and you have a carboxylic acid and you slap them together. Okay, you use sulfuric acid as a catalyst, but the reaction is an equilibrium reaction, meaning it's going back and forth. So this is not the best way to prepare things. You can do an alcohol with an acyl chloride, right? An acid chloride. That'll also give you an ester in the presence of pyridine. So this is a much better way to do it. So you use the alcohol and the acid chloride instead of the ester or carboxylic acid. Then for a nitrate ester, you use nitric acid, and you basically form this ONO2, which is a nitroester. If you do it to glycerol, you form nitroglycerin, which is explosive. And then finally, phosphate esters, you have phosphoric acid, and that can basically hook on there and form a phosphate group. And this can happen multiple times. Okay, so that phosphate can hook onto all of this. All of these OHs can get replaced with whatever you're treating it with. Now, this is an important reaction in biology because phosphate esters form the backbone of DNA. Okay, so you know that double helix, you've got the bases pointing out right across the way, and then this is that backbone. It alternates sugar, phosphate, sugar, phosphate. So in biology, phosphate esters are tremendously important. So last thing, alkoxide ions, Williamson ether synthesis. Basically, you have a primary halide or a tosylate. You hit it with an alkoxide ion and you form an ether. We've looked at this one before because it's just an SN2 displacement. You're just using alkoxide ion as your nucleophile and doing an SN2 reaction. It's pretty much that straightforward. If you have a secondary or tertiary alkyl halide, then you get an elimination. So this only works, you only get ethers if you're doing it on a primary carbon. So keep that in mind. Okay, so I realize I went through that quite fast, but a lot of it is stuff we've already talked about. It's just a couple more reactions you can do with alcohols. Again, most of this is important for you to have in your toolbox when you're working on a synthesis problem. So I'm going to recommend you look at the, I got to double check the page number. I'm going to recommend you look at the summary starting on page 546 and going to page 550. It basically summarizes everything in this chapter, all the different reactions. Okay? Practice one or two of the mechanisms, but a lot of them are very similar to what we've done before. Okay? It's carbocation, SN1, SN2, E1, E2. It's the same stuff, just different reactants, right? You're building the same thing using different Legos. And there is actually quite a useful guide to doing synthesis, starting on page 543 and going to page 546. So I recommend, if you're having trouble getting your mind around synthesis, to read that box, because it has a helpful step-by-step, how do you start a synthesis problem? How do you approach a synthesis problem? What do you do with it? Okay, but let's work some problems. So on page 511, question 11-2, predict the products of the reactions of the following compounds with chromic acid or PCC with tempo. Okay, so A, We have cyclohexanol. Okay. And chromium. So PCC, right? So if it's a secondary alcohol, then they're both going to go to the ketone. The cyclopentylmethanol. So here, if I treat it with PCC, I'll get an aldehyde. And if I treat it with, I'm just going to put chromate. So if I treat it with PCC, I'll get an aldehyde. And if I treat it with chlorate, or chromate, geez, you'll get a carboxylic acid. Cyclohexane, both of them. Sorry, that's ACE. Oh, this is all out of order. Cyclohexane, you're going to get nothing. These guys do not react with alkanes. 1-methyl cyclohexanol. Right? I've got a tertiary alcohol. How can I oxidize that? I can't, so you're going to get no reaction. That's B. D-cyclohexanone. So that's as oxidized as it can get. So no reaction there either. We did F. 1-phenyl propan 1-ol. So 1-phenyl so propan 1-ol 1 phenyl. That's a secondary alcohol, so PCC or bromate will do the same thing, right? The only difference is if it's on a primary, so. Hexan 1-ol. Here, G. Hexan 1-ol, right? PCC. 4, 5, 6. Give me the aldehyde and chromate. 4, 5, 6. Will give me the carboxylic acid. And finally, acetaldehyde. Acetaldehyde, yeah, you hit that with PCC, nothing. And you hit it with chromate, you're going to get acetic acid. All right. Go to page 513, 11.5. Predict the products you expect when the following starting material undergoes oxidation with an excess of each of the reagents below. So, we're going to put this guy in the center. Okay, so chromic acid, PCC, let's see, GMP, Wern, Okay, so the thing is, PCC and SWERN, which is the MSO and oxyl chloride, and EMP, will all give you the same product. So this is the mild version. Right? Tertiary alcohol can't get oxidized. This will become a ketone. That'll become an aldehyde. Okay? Chromic acid and the NaOCl with tempo, that again, tertiary can't be oxidized. Secondary becomes a ketone. That becomes a carboxylic acid. Okay. Page 518, 11.9. Predict the major products of the following reactions. Ethyl tosylate and tert butoxide. So ethyl tosylate and tert butoxide. Now, the question is this going to replace the tosylate, or are you going to get an elimination? So, bulky base like that, right? Tons of bulk is going to favor elimination. Okay, so you're probably just going to get ethylene. Isobutyl tosylate and sodium iodide. So here we have a primary tosylate, so that's likely just going to give us a substitution. Remember, bulkier things favor elimination, less bulky things favor substitution. R2-hexyl tosylate and sodium cyanate. Or 6 R2 also would be 1. That's R. Okay, so and sodium cyanate. Okay, so we're going to get a substitution. It's secondary. So if we get SN2 substitution, then we're just going to get inversion. Tosylate of cyclohexylmethanol and excess ammonia. That's that. And then N-butyl tosylate. Sodium acetylide. Okay, that's just going to be pretty straightforward substitution. That's it. Tosylate's a leaving group, so it's literally just the nucleophilic substitution again. All right, page 526, 1121. Give the structures of the products you expect when each alcohol reacts with HCl, CnCl2, HBr, PBr3, PI2, and SOCl2. All right. So butan 1-all, 1, 2, 4, H. Okay, so the first thing is Cl and Cl2. Second thing, Br, Br3, PI2, and SOCl2. Okay. So with HCl, ZnCl2, you're gonna, I mean, obviously, you're gonna get 1, 2, bad yield. HBr, bromine, PBr3, bromine. Although, right, HBr could give you elimination, so this one could give you, right? PI2 and SLCl2. Right, so these three will give you the substitution every time. These two could get funky. Methyl butan 2-all. All right, so now we're working with a tertiary alkane. So your tertiary, your tertiary alkane is a pretty easy substitution. So that one, probably not going to see any difference. Right, so tertiary alcohol is pretty easy to do the carbocation, no rearrangement. Probably not going to get elimination. So this one's a pretty safe bet. 2,2-dimethyl butan 1-all. All right, so now here's where you could easily get rearrangement, okay? So if you form a primary carbocation here, right, this guy is going to shift over. So for HCl and HBr, okay, get rearrangements. For PBr3, don't get a rearrangement. And finally, cis 3-methyl cyclopentanol. Cis 3-methyl cyclopentanol. So cyclopentanol. HCl, Br. The secondary, so they shouldn't have any issue, and there's you can't rearrange. Right, there's nothing to shift over. That's on the adjacent carbon. Then so Cl2, same product. PBr3, that product, and then Bi2. We'll give it the iodinated product. All right. Now to page 536. Question 1130. Predict the products formed by periodic acid cleavage of the following thiols. Okay. So remember, periodic cleavage will cut right down the middle, so you're going to get symmetrical product, right? That side and that side. Okay, I'm going to cleave here. So you'll end up with that and that. And once again, we're splitting here. So I've got phenyl attached to a carbon and another carbon. That's a ketone. Okay, so that's 1, 2, 3, 1, 2, 3. That becomes a ketone here. I'm going to get an aldehyde with 1, 2, 3 carbons. 1, 2, 3 carbons, aldehyde. Okay, so that's if you draw it out and count the carbons, right? So the easiest way to make sure your split products, and this is not just for for this cleavage, to make sure that anytime you have a cleavage that your products are correct, count the carbons. I mean, I'm just a phenyl group, but so phenyl group, and then 1, 2 carbons, and this oxygen turns into a ketone. And here I have 1, 2, 3 carbons, and that oxygen turns into an aldehyde. All right, so that's chapter 11. It's not that much more stuff. It's a couple more. It's a couple more. It's a couple more. Words hard. A couple more reactions in your toolkit. A few unique things, but mostly probably the most important thing in this is tosylation, because tosylation is a way for you to very easily get rid of an alcohol, substitute it with something else that you want that's more. It's such a good leaving group, so you can turn any alcohol into a leaving group just by tosylating it. So, yeah, the important things are the manipulations of alcohols and how that applies to synthesis. So, all right, one more chapter left, and then you are done with the first semester of organic chemistry.